Fleetwood Mac this morning to bring a smile to your face.
You're lifting me up.
You're lifting me up, people.
Never let me down.
You never let me down.
Unless far, whenever you're around.
Oh yeah, I do smile every time I see you.
When I've got a feeling.
Good job, Sophie. Move that head.
It'll work out right. Can't stop thinking about you every day and night.
Here we go, people.
Ooh, I got a love, I got somebody's love, got a hold on me. Yeah, I got a love, I got somebody's love, got a hold on me.
Good morning, class, or afternoon if you're in a different time zone. I'm Kim Sutton, coming to you from rainy Humboldt County. We're going to have a week of rain, which is fine. That's what makes our redwood trees grow and our ferns grow. I've always wanted to do a topic of Digital Root, and I know many of you that have been with me before, you have heard me talk a little bit about it in workshops, maybe a snapshot here, snapshot here, but I want to add to it today and give you some concretes. And trust me, I can't teach you everything I know about it. I wrote a book a while back about digital roots. It's called The Power of Digital Roots. And what's funny about this book, if you read the introduction, I have a letter to the teacher that says, really don't think you have to know everything about digital roots before you teach it to your students. My hope is that by hearing me talk about it, and we'll work through some problems, you'll have a sense of, number one, what it is, and number two, why you should teach it. So I'm not going to do any bells and whistles. I'm just going to introduce it to you in a couple of different ways and have you work through some problems. So hopefully you have some paper and pencils or something to write with, because it always is helpful if you're not just watching me, you're kind of looking at the potential of Digital Root. So one of the things I said in my introduction to the book was, I'm always flattered when people say, Kim Sutton invented Digital Root. I think that's so funny. I'll be walking through a conference hall, like when I speak at the CAMP conference in Texas or California conference or the Northwest Math Conference, and I'll be walking through and someone will say, oh, there goes Kim Sutton. She invented Digital Root. And it just cracks me up because I didn't invent it. I couldn't invent it. It's a property of a number. So first thing, if you're taking notes, put a note to yourself, Digital Root is a property of a number. And then I'm going to say this probably 15 times during the presentation, it's not a trick. I don't believe in teaching tricks. So Digital Root is not a trick. And I prefer you not teach tricks to children because it becomes a little bit like a magic show. Only the magician has the magic. And that's not true about Digital Roots. So I'm going to switch off my document camera right now, just so you can see on the screen really. Oh, I say that and then I'm struggling to do that. Oh, thank you, Josh. Up here. This happens to me all the time. I'm getting better. Gotcha. Okay, there we go. So hopefully you can see that behind me, I have two number property charts. This is a routine that I do with children every day. So it's a way for us to look at the properties of numbers. Now, if you get up close to this, which I don't know if you can zoom in or zoom out, it starts off very basic, even and odd, multiple of 2, multiple of 5, multiple of 10, single digit number, two digit number, three digit number, less than, greater than, digital root. Our number is between, closer to, and what is the expanded form. If you look at the challenge, which is what I do with 4th, 5th, and 6th grade, still even and odd, but the language changed from multiple to factor, and my factors expanded. I also include prime and composite, digital root, numbers between, closer to, expanded form. Now, I'm going to go back to my share, and I want you to think about that list as a practice with students, something they could do on a regular basis. So that first one, the basic list, is what I would do with primary children, K through 3. And then the challenge list is what I do with 4 through 6. So imagine a routine as you count to the 100th day of school, where every day you're finding digital roots. So I'm going to take you into this because I want you to leave with the most important message, which is why you should teach this with children. But let's go into digital roots on a really basic level. So this is the one area of mathematics where children will learn how to find the digital root before they understand what it means. I wish I could flip that, because most of you know I trained with Marilyn Burns. So I'm big on teaching for understanding and then taking the shortcut. But the problem with digital roots is children will see the shortcut before they have the understanding. And I wish I could change that, but I can't. So I'm just going to allow it to happen. So right now, let's just get comfortable with the fast, lazy way to find it. So let's take a number like the number 10. And if you were watching yesterday when I did the game session for upper grades, I ended with this little example because someone asked the question, how do you find it? The fast, lazy way is to simply add the digits together. So 10 has a digital root of 1. Fast and lazy, any kindergartner can do that at some point. I don't have to explain why they need to know it. We just practice finding it. They love knowing the little tiny piece that they know, which is this. So let's find the digital root of 23. All you're doing is adding the digits in the number. So 23 has a digital root of 5. Not hard math, is it? Let's do another one. Digital root is 71. Mouth it for me. You're right. It's 8. Kind of no-brainer. So let's go a little deeper. Digital root of 123. Mouth it. Pretty easy math. Now to find that, all I did was add the 1 plus the 2 plus the 3. So you could call that the sum of the digits, but the problem is, if things are important in this life, we give it a name. And you're about to learn why digital root is so important for children to know. But let's go back to finding it. So let's do 561. So this is where we have to realize the only possible digital roots of numbers are 1 through 9. So let's find digital root of 561. 5 and 6 is 11, and 1 more is 12. That's not a digital root. So if you get a 2-digit sum the first time you add, you're going to add the digits in that sum. So this is what we call a 2-step digital root. First time we added, we got 12. I can't stop there because the digital root's a single digit sum. So the digital root of that number is 3. Are we doing okay? Give me a nod. Holly's giving me a good nod. Here's the thing about this. Let's practice another 3-digit just for the fun of it. $953. First time I add, I get 17. That's not a digital root, so I have to add again. That digital root is 8. That's another 2-step digital root. So the only possible digital roots for numbers are 1 through 9, even if the number had 17 digits. It would collapse down to a single digit sum. Now, here's the thing. If I stop right there and just have them find it, I haven't gone far enough because it looks right now like a trick. So let's go deeper into the mathematics on this. I wrote all of these numbers in base 10. And at my workshops, I always ask all of you, what does base 10 mean? And I go around and I listen to my audience describe what base 10 is. We think that base 10 means making groups of 10. That isn't what it actually means. Put a little reminder to yourself. The number of the base, and we work primarily in base 10. Greg Tang loves to have people work in other bases. I do too, but it's not easy math. So base 10, the number of the base, tells you how many symbols there are in which to record quantity. So remember when I had you, those of you that have been with me for some of the classes, I had you label as a startup activity index cards with the digits 0 through 9. That, if you count those symbols, in base 10, there are only 10 symbols. So the number of the base simply tells you how many symbols there are in which to record quantity. So base 7 would mean 7 symbols. And those symbols, watch my fingers, are 0, 1, 2, 3, 4, 5, 6. How many fingers am I holding up? 7. So there's only 7 symbols in base 7. So the number of the base tells you how many symbols there are in which to record quantity. Now, some of you have been with me when we have made a place value odometer, like the odometer in your car. So if you were to take your car apart, or if you were to go to a junk, a salvage place and ask for an odometer out of a car, what you would see is a strip with the digits 0 through 9. And they roll through each place to tell you how many miles you've driven. So if you've made my odometer, that's from my place value book. The nice thing is, children get a sense that there are only 10 symbols, 0 through 9. After you get around to 9, there are no new symbols. So when we're teaching a child what's 1 more than 9, we have to get them to understand that now when they write the 1 in the tens place, it means one group of the amount that is 1 more than 9. Why am I going like that? Because this is where it gets a little deeper mathematically. So what was the digital root of 10? 1. What this really means, and I'm going to go slow here, is in base 10, digital root shows what remains in a number after you take away all the groups of 9 from that number. Why 9? It's the largest symbol in base 10. Now, nobody gets that the first time I say it, so just be patient. Let's try the number 23. That was the second number we did. It has a digital root of 5. What's that actually mean? It shows what remains after we take away all the groups of 9 from that number. So let's take the number 23. Is there one group of 9 in 23? Yeah. Are there 2 groups of 9 in 23? Yes. Are there 3 groups of 9 in 23? No. 2 groups of 9 would be 18. If I take that 18 away, I'm left with 5. Now, I still haven't given you a reason to teach that. So my reasons are coming. I just need you to understand the fast, lazy way to find digital roots is to add the digits together. This wouldn't just work in base 10, people. It would work in any number base, but it wouldn't be the removing of groups of 9. It would be the removing of the greatest quantity or the greatest symbol for that quantity in that base. Now, you're a brave group to be here on a Wednesday morning because this is heady stuff. Kids love it because it's something new and different, and especially when you give them a reason to know it. Let's go back to exploring the removing of groups of 9. So let's take the number 71. It has a digital root of 8. How many groups of 9 are there in 71? 8 groups of 9 would be too many, wouldn't it? So it's got to be 7 groups of 9. 7 groups of 9 is 63. When I take 63 away from that number, the 8 shows what's left. That's its digital root. Honestly, these Zoom meetings are so funny because in a classroom, I can kind of read your faces, so I can know whether to keep doing the same thing or kind of move on. But let's do one more. Let's just, for the fun of it, let's do the number 102. Fast, lazy way to find digital roots. Add the digits. I mean, that's kindergarten math now. I'm not saying the removing of the groups of 9. I mean, just adding the digits together. So this number has a digital root of 3. What it's really telling us is when we take away all the groups of 9 from this number, there's 3 left. So let's think, in that wonderful brain of ours, how many groups of 9 would there be in 102? To me, I think it's 11. So 11 groups of 9 would be 99. What would be left after I take away 99? It'd be that 3. Should we try a harder one? Say yes, Miss Sutton. Let's do 4,613. So fast, lazy way to do digital roots. I'm going to add the digits together. I see a 10 plus 4 more is 14. That's not a digital root. So I have to add one more time. That number has a digital root of 5. Now, if that means I take away all the groups of 9 and 5's left, let's find out how many groups of 9 are in that number. I don't know and I don't really care, but I can figure it out. So let's do it as a division problem, just to prove the point. So let's see. Oh, 99, 11, I think it might be 12. 12 groups of 9 is 108. That's what's left. So let me capstone this. I still haven't given you a reason to teach it. Right now it looks like a trick, but I'm going to invite you into the 2 reasons why it's important to teach digital roots to children. Here's the thing. Let me go back and be succinct about what it really is mathematically. Put a note. Base 10 means there are 10 symbols. The greatest symbol in base 10 is 9. After 9, we have to recycle and reuse those digits to stand for groups. Now, some of you know that I always hold up my friend Stuart Murphy's book, Earth Day Hooray, because the children on the cover of the book are recycling. Ding, 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 ding. Place value is recycling those symbols. There are only 10 symbols. Largest symbol is 9. Then we have to start over and recycle and reuse. So here's what digital roots really mean. Digital roots show what remains in a number after you take away all the groups of 9 from that number. So Josh will let me know. He looks like he has a good question.
So how does it work when the number is evenly divisible by 9?
Ah, I am so glad you're paying attention. So who'd that question come from?
Catherine.
Catherine, I love it. So here's the thing, and I write about this in my book because Catherine just did the hard work. She goes, what happens? I'm going to contrive a number for you. So here's a number, 5,418. The digital root of this number, first time I add, I get 18. Second time I add, I get 9. Here's the thing. I picked a number that you could visually chunk and tell is completely divisible by 9. So if I were to divide this by 9, my quotient would be 602. No remainder. So there's nothing left over. Put a reminder to yourself. A digital root of 9 is the same thing as a digital root of 0. Here's where we're going to go with this. I want you to hang that because Catherine brought the question up. I'm going to come back to it when I go into the second reason to teach digital roots. So just hang with the thought. A digital root of 9 is the same thing as a digital root of 0. you just would never add and get a digital root of 0. Just hang with that for a second. And I know I will come back to it when we talk about factoring. So there's 2 reasons to teach digital roots to children. You ready to work hard? Let's say you give them a worksheet. I'm going to pick 3rd grade, and I'm going to pick what I might give to a 3rd grader if I had a headache and I wanted them quiet for a little while. So I might give them a page. If I had taught this and we are reviewing, I might give them a page of problems that look like this. So I want to know, do they remember how to do the regrouping, apply any strategy that I've taught? Here's the thing. I'm going to do this in about the amount of time a competent 3rd grader would do this problem. And I'm going to do it with the mumblings of what I recently heard a 3rd grader do with this problem. So I walked in the room. Teacher was relinquishing her classroom to me. I was going to teach something, not this, but they had a little worksheet out in front of them. So I'm standing by this young man named Brent, and he does this. Okay, I always start in the ones place. 1 here, and a 1, put down a 1. I put another 1 up here. Oh yeah, my teacher says that's not a 1, that'd be a 10. So now I'm adding my 10s. Okay, that makes a 10, 17, put down a 7. I carry a 1. That 1 is not 1, it's 100. Those would be 4, 5, 6. Now, here's the thing about that. Most of us have a knee-jerk reaction to this, and I don't mean the way I did it. That's not what matters. On a problem like this, what matters is that you have the correct answer. That's the kind of problem that is. So our knee-jerk reaction to this is we will say to children, check your work. Come on, check this. What do we actually mean? Do we mean do it again? Because have any of you ever tried to edit your own words? I find it extremely difficult. I know what I wanted to say. In my mind, I said it. When my daughter edits my work, she'll go, Mom, you left out the word and or the, or here's the thing about that. Ooh, is this modular math arithmetic? Who asked that one? Modular arithmetic, I'll address that. Josh handed me the paper. I'll come back to that because that goes, boy, we're going to have a lot of these Zoom sessions. Here's the thing. One of my student teachers said, well, I would want that 3rd grader to write this problem on a piece of scratch paper and write it as a subtraction problem. Look at my face. Am I still smiling? Here's my answer to that. Good luck, because a 3rd grader copying this problem over on scratch paper, it's not even going to be the same problem. Also, if you're doing the inverse operation, what child do you know loves to subtract? They don't. Thank you, Amy. I love watching your head. So here's reason number 1. Put a note. Digital roots can be used for checking. All, please hear me, all, please hear me, all computation. So let's find the digital root of our 2 add-ins. And you know me, I love academic vocabulary with children because if you say it and they see it and you say it some more, they will learn it. So let's find the digital root of 375. I see a 10 plus 5 is 15. I can't stop there. This number has a digital root of 6. Let's find the digital root of 296. Now, here's the thing. Later on, I'm going to show you even a faster way to find digital roots. that allow you to really be lazy mathematicians. So the digital root of this number is 8. First time I added, I see 11, 6 more is 17, 1 and 7 is 8. What operation did I do in the original problem? I added, so now I'm going to add my digital roots. I get the sum of 14. What's the digital root of 14? It's 5. Let's go now and find the digital root of our sum. 6 and 7 is 13, and 1 more is 14. 14 has a digital root of 5. If your digital roots match, you've done the problem correctly. Woo, woo, woo. Anybody excited? Put your hands up. So put a note. You can check all 4 operations with digital roots. So right now, I'm going to jump to multiplication. I'm going to come back to subtraction because the inverse operations are a little bit different, but not troublesome at all. So let's go to multiplication. Let's take my age, 37. That was a math joke. You're supposed to be laughing. Times 56. Now, I'm going to admit a bias here. I think we go to this algorithm that we were taught to do this problem with way too early. Because what's the most commonly made error in this problem? It's always the placeholder, if you call it that. And we taught a very much of a process, a rote process, instead of a deep understanding. So I can no longer even do that algorithm, or I won't give myself permission to do it. So watch what I'm going to do here. I ask a child, if the problem is 7 times 6, how many times would you multiply? And they always go 1 time. If the problem is 37 times 6, in a standard algorithm, I'm talking about the standard algorithm, you're actually multiplying twice, aren't you? You're multiplying your 1s, then you're multiplying your 1 times that number of 10s. If I add a digit, you multiply 4 times. Here's the thing, I'm not going to go to the algorithm before they understand what they're doing here. So if you're bothered by me doing this, this is really the way I teach it. The algorithm, they gratefully accept, but later on, when they understand this with place value. So let's multiply 4 times. If I really wanted to be controversial today, I could tell you that if I know place value of a number, it doesn't matter where I start, but I'm blowing you away enough with digital roots that I'm going to do it traditionally. So let's do our 1s times our 1. So 7 times 6, 42. Then, and this is where I always cut student teachers off on this, because they'll stand at the board and they'll go 6 times 3. That is not a 3. You have to think at all times about place value, or mathematics and algorithms don't make sense. So this is 6 times 30. And if you're from a Common Core state, and not everybody watching is, but you know, even if you are sitting watching in Texas, you know your TEKS do some layering, some scaffolding of skills where children practice multiplying single digit by a multiple of 10. That's what that practice is for. So 6 times 30 is 180. Now let's move to our tens place. I have 5 tens times 7 1s. That's 350. 50 times 30, 1,500. Now, some books like to call this partial products. I'm going to be honest with you. That label was made up by textbook companies. Mathematicians don't call that partial products. What they say is this is best practice, because you will never miss that placeholder because you're always thinking place value of what you're multiplying. Now, if a child goes to this much work and they finish it and hold it up for you to come over and you scream at them, check your work, I doubt you're going to light any mathematical fires. So let's check it with digital roots. I'm watching some of you drink out of a coffee cup and I'm like so jealous. It just made me want a cup of coffee. Oh, that's adult attention deficit disorder. Sorry. So what's the digital root of 37? First time you add, you get 10, it'd be 1. I love when my upper graders would go, Miss Sutton, I see it. 4 times 9 is 36. That's 1 more. So they're looking at this for those groups of 9. If you just teach it as a trick, they never recognize how connected this is to place value understanding. So what's the digital root of 56? Hold up your fingers. It'd be 2, wouldn't it? What operation did I do in the original problem? I multiplied. Ooh, I like the hand signals. Good job, Sophie. So I'm going to multiply my digital roots together. Now, was that check hard math? Say, no, Miss Sutton, no. I get a product of 2. Now I'm going to go down here and I'm going to check the digital root of my actual product in the problem. 2 and 7 is 9, plus 2 more is 11. It has a digital root of 2. So if these digital roots match, then I've done the problem correctly. Josh is writing a question down, and it may or may not be this one, but this is usually where someone will raise their hand and say, yeah, but couldn't a child mathematically be off enough to have your digital roots match, even though they did the problem incorrectly? So I asked one of my favorite mathematicians this question, Dr. Arthur Wiebe, and he laughed, and he laughed. He goes, Kim, most computational errors are not far enough off to bring it back to the same digital roots. It almost statistically won't happen. So just think about that for a minute. Now, would you, just so I didn't contrive a problem that works, would you take a 2-digit number now and another 2-digit number, and would you multiply initially so you get the product, and then would you check it with digital roots? So when I'm feeling lonely and I miss all of you, I make up these problems so that I can check them, just so I won't miss you too bad. Miss Sutton, you really should play a song while we work on the problem. Shall I do that, class? Josh says, yes, give us a song, Miss Sutton. All right, work to this one. Good song. intentionally made an error here. So when I did this just to show you. This product has a digital root of 5. When I checked it, I got a digital root of 3. So something's off here. So I'm going to go back and check my digital roots. Oh, I caught it. The digital root of 16 is not 6, it's 7. 7 times 2 is 14, which has a digital root of 5. And this number has a digital root of 5. Did it work for your problem? Josh is checking. If it didn't work for your problem right now, shoot me an email. Josh is watching, and I will happily work your problem. It's all working. Oh, good. This is a good day. Now, let's take on subtraction, because people love to tell me subtraction doesn't work. Look at my face. Am I still smiling? Here's the thing, people. If it works for addition, subtraction is an inverse operation. It would have to work for subtraction, but you have to think differently. So right now we're going to kind of flex our little muscles. So I'm going to just do a very simple subtraction problem here. When I do this, I think my answer is 42, but I want to check it with digital roots. So, digital root of 71 is 8. Digital root of 29 is 2. What operation did I do in the original problem? If I subtract it, I get a digital root of 6. That problem worked out great. But I'm going to tell you, they don't all work out like that. So you're ready to be challenged? So some problems will do this just great, but I don't want it not to work for a child. So I teach it differently, and I'll show you where this is in my book so that you can see. Let's do a problem 101, take away 79, or the difference between 101 and 79. A little more complicated problem because a child has to subtract across zeros, but let's say this child can do that and gets 22. So I'm intentionally setting this up for you. This one worked great. This one we're going to have an issue with. What's the digital root of 101? It's 2. What's the digital root of 79? Oh, I love the fingers up in the air. Good job, Sophie. Here's the thing, people. I paused there because you're going to see you can quickly find digital root without doing it as a 2-step. But I'll leave that hanging for a second. It's 7. Now I've got a really big problem because the digital root of this is 4, and I got to make this make sense. So here's what we know. And if you've been with me before, you know I talk about triangular flashcards. A triangle flashcard, as opposed to a rectangle flashcard, allows children to practice not one question, which is what a rectangle does, but it allows you to practice 4. My hand controls 7 plus 4, 11. 4 plus 7, 11. 11 take away 7, 4. 11 take away 4, 7. So in that triangle, I'm doing the association of inverse operation. Please be aware, I'm not a big person for saying fact families. That just to me is a little too fluffy. Even with little guys, I call it an inverse operation. So let's go back to our original problem. If you were setting this problem up, you have three numbers. It's set up currently in a subtraction problem. If you were going to set it up as an addition problem, what would 101 be? It'd be the sum, wouldn't it? And these two would be the add-ins. So the real way you check subtraction so that it works every time, and I talk about this in this book, is you identify the add-ins in the problem and you add up. So if I took these three numbers and made them into a subtraction problem, this would be an add-in, this would be an add-in, and this would be my sum. So the real way to check subtraction is to add up, because sometimes it comes out perfect like this, but children are going, Miss Sutton, it doesn't work here. Yeah, it does. So let's add up. 4 and 7 is 11, which has a digital root of 2. So right now, just for fun, because I can tell you're having so much, let's check it for a subtraction problem. So let's make, I'm just picking something that I know will have a little bit of regrouping here. Oh, that's a good one. So would you do that problem? And let's see what happens. Did you get the same difference that I did? Good job. Love seeing the shaking heads. Now, here's the thing about this. No child doing this subtraction problem wants to do it again to check themselves. They're done. They're finished. They're toast. So here's the beauty of digital roots. Digital roots, fast, lazy way to check. So what's the digital root of 424? Looks to me like it's 1. Is that what you got? Digital root of 179. Teacher pauses because she hopes her students see a shorter way to find digital root. And then when I find the digital root of 245, I get 2. Now, if I were trying to check it by subtracting my digital roots, I'd have a big fat mess. But if I know these three numbers could be arranged in a triangle, this would be add-in, this would be add-in, this would be sum. So I'm simply going to add up. That's what I modeled in this book to give students clarity of inverse. You know what one of my students said? And man, this earned us a pizza party. He goes, hey, Miss Sutton, did you notice when we're adding, the arrow went this way? When we're subtracting, you're adding up. It's the opposite arrow, and subtraction is kind of the opposite of addition. That's pretty exciting, people. So when I add, I get that digital root for the sum, the same as part plus part on the digital roots. Now, this leads us to division. Here's what's funny about me doing this, and I'm not a numbers person, you know, I could care less, but we started with a bunch of people and we dropped down because sometimes this pushes us. But I did want to get this up on my website because I don't think the first time you hear about digital roots, you can make all the connections. It's not till later that you start to chew on it. So if your brain gets tired, trust me, you can always go back and chew on it. Should we try division? Say yes, Miss Sutton. Now, I set you up to be good problem solvers because we just went through the fact that subtraction is the inverse operation of addition. What we know about division is it's the inverse of multiplication. So keep that here. Now, I'm going to intentionally do a problem. Let's see if I can do this off the fly. I could have done my homework last night, people, but I didn't. So I'm going to make a divisor of 23, and I'm going to go ahead and make my dividend. I'm doing this intentionally, okay, to come out nice and even. So my dividend is 4,669. Now, keep the what if question, because here's the quirky thing about division. You might get a remainder. So if I'm showing you something, there can't be an exception to the rule. Here's the thing. I live by this guiding principle right here. Mathematics is filled with constants. Because these are things, and digital root is a constant, that really allow children to problem solve. So let's do this on a problem that's going to come out in a nice, neat package. So if we were doing this, and I can model it using partial quotients, but I'm just going to do it to model division with digital roots. So I know that in 4,600, there would be 200 groups of 23. Pardon my language, because the algorithm would say, cover all this up, you slide it over. How many 23s are there in 46? But it's not really 46, it's 4,600. And this isn't a 2, it's going to end up in the hundreds place. So if I ask myself how many groups of 23 are there in 69, I believe that answer is 3. And this comes out in a nice, neat package. So I'm going to do the one with no remainder, and then I'm going to show you that, of course, it works with a remainder. So let's just get playful. Let's take the divisor, and let's find the digital root. Easy math, it's 5. Let's take the dividend and find the digital root. A little harder because you have to add 4 numbers, or maybe you've discovered that you really can be lazy and you're really not having to add 4 numbers, but I haven't gotten to that yet. So the digital root of this would be 7, I believe. Is that what you got? Okay. And this digital root is 5. Now, right now, this looks like there's no way you're checking, but you really are. I want you to think about that triangular flashcard, and Catherine is watching this after I did triangular flashcards with her parents and teachers on a virtual training a while back. And here's the thing. We know that the triangle also works for the operations of multiplication and division. So I'm just modeling something quickly to make this big connection to you. My hand controls the question. 4 times 6, mouth it. 6 times 4, mouth it. 24 divided by 4, mouth it. Good job, I like the hands up. 24 divided by 6. So Division is an inverse of multiplication. So let's go back and look at our numbers. If I have these three numbers and I turn them into a multiplication problem, my two factors would be 23 times 203. My product would be 4,669. So now think of multiplication and division being inverse operations. I've identified my factors. This number is my product. So if these are factors, I'm going to multiply my digital roots. 5 times 5 is 25. What's the digital root of 25? 7. So it works. But here's the quirky thing. Miss Sutton, what happens if there's a doggone stinking remainder? Well, I don't know. Let's try it. So let's try one with a remainder. I'm going to take the divisor 51. I'm going to try not to make the problem as hard. And let's do the dividend of, oh, here's a good one. What's funny is I actually used digital root to get that. I'm so proud of myself. Sometimes I'm my own best audience because nobody's laughing with me except Josh. He's laughing over there in his camo hat. So here's the thing. I'm really going to do this rather quickly just so I can see if I made one with a remainder. So in 700, how many goes to 51 are there? Okay, there would be, there's not enough to make two. I get this, I get this, I bring down this, okay? Now, I know that this is close to 50. 4 groups of 50 would get me 200. So it's not 4, it's going to be 3. So I did set this up. 3 times 51 gives me 153. I think I did that correctly. Anybody checking me? How am I doing? Now I subtract and I get a really large remainder. Now, we know we convert remainders to fractions and then decimals, but I'm just going to keep it as the R thing because I got to prove a point with you. So I'm going to take a different color pen just so you can visually see this. If I know division is inverse of multiplication, I have to identify my factors and my product. So in this problem, 51 is a factor, 13 is a factor. When I multiply them together, I don't get 709. I have to add in, please hear me, I have to add in that remainder because it's that much more to make 709. Now this one takes a little thinking. It's not going to happen fast, and I'm going to do it kind of fast, and then I'm going to have you do one. So what's the digital root of my divisor? It's 6. What's the the digital root of what would be my quotient, which in essence, if I turn it into a multiplication problem, it's another factor. It has a digital root of 4. Now this is where people go, oh, well, what do you do with your remainder? So I told my kids, I'm not going to tell you, I want you to think about it. And what I loved about it with 4th and 5th graders is they kept going back, and it reminded me, I must have gotten through on something, that this is the add-on to it, okay? So just breathe, everyone breathe. If these two are factors, I'm going to multiply those two together, and I get a product of 24, which has a digital root of 6. We know this number has a digital root of 7. So here's the thing, they don't match. But I haven't done anything yet with that add-on, which is the remainder. Here's how cool digital roots are. Can you tell I'm excited? I'm pretty excited. You could add 46 over here to that digital root. I could add it there, and I'd get 52, which has a digital root of 7. But I'm so lazy, people. I don't want to add 46. So I'm simply going to add the digital root of 46. What's the digital root of 46? It's 1. So if I add 1 to this digital root, it's going to be 7, which is the same as the digital root of my product. Now, here's the thing about it. That was kind of heady stuff. So would you just take a minute? Would you make yourself a 2-digit divisor? Josh just held it up and said, it's 12 o'clock. You've been talking for an hour. And we haven't even got to the second reason. So would you make a 2-digit divisor and a 3-digit dividend? And would you check yourself? And if it doesn't appear to work, I will perform for you as the trained seal that I am. So would you work the problem? And I'll keep it nice. Little background music. An instrumental from Ron Brown. Does anybody have one that's not working out? Okay, that's, yeah. You're the best class ever. Does anybody have one that didn't work out? Isn't that a nice song? It's called Peaceful. It's from Keep It Moving by Ron Brown. Now, I know I lost a couple of you. Would it help if I did one more? Josh is looking at heads, or have you got it? Sophie, would you like one more? I can only see 3 people.
I'm still working on it. Just, I need a second. I need
Okay, sorry.
No, it's all good.
Yeah, they say they don't need another one, then 497 divided by 26.
497
Yes,
divided by
equals 12.
26.
Ugh.
So I don't, who wrote that one down so I can personalize this a little? Josh is working on. So let me walk you through one more and I'll go slow. Remember, you're going to have access to this video to watch it again. I knew we'd chew up a fair amount of time on this, but it is a powerful concept. But if somebody teaches it to you as a trick, there's no power in it because it's not a trick. It's all about place value understanding. So let's try this one. And again, I'm asking myself, how many groups of 26 are there in 497? I can think about that. There's 10, 26. That's a good problem. Now, I know I'm asking myself, how many groups of 26 are there in 237? It's not 10. 9, 5 would be, let's say I try 6, 7, 8. 8 gets me awfully close. I'm gonna try 8. So why'd I think 8 was close? Oh, that's right. 48, 16. It's a lot of pressure to do math while people are watching. Now, should it have been 9? It should have been 9. I have no problem making mistakes in front of people. So 9 would be 54, carry the 5, 23. Oh, I like that problem. And it came out with a nice little 3 remainder. Is that right, Miss Tracy? You're watching? Okay. So my quotient is 19, remainder 3. So if I were going to turn this into a multiplication problem, this would be a factor. This would be a factor. If I multiply them together, my product is 494. I have to add in the 3, right, to get 497. So I'm going to treat it as a multiplication check. What's the digital root of 26? 8. What's the digital root of 19? It's 1, isn't it? Oh, I like when it's a fast, easy way to check. Now, because these were factors, I multiplied these two together. So I'm multiplying my digital roots of my factors together, and I get 8. Now, here's the problem. I've got 3 more. So I can add in the remainder at any point or add in the digital root of the remainder at any point. So I'm going to add it in here because that's what it is. It's an overage to reach that. It's what's left over. And the digital root is 11, which has a digital root of 2. So now I check it here. What's the digital root of 497? 2. Are you happy? Say, yes, Miss Anna, I'm really happy. Good job, Tracy. That really helped me. Did that help? Here's the thing. When I wrote the book, I tried to use a bunch of humor in the lessons because I want you to read the lessons to the students. I want you to say to them, I'm learning about digital roots. I don't know it all. I know that this pattern is very helpful. Now, let's go to the second reason to teach it. Otherwise, I'm going to be here all day and you're going to go, I got a job to do. So many of you saw me do a lot of math with the pattern sticks. Put a note to yourself. The second reason to know digital roots is you can determine or eliminate factors of numbers just by finding the digital root. So if I take, and a lot of you know I have a book called Powerful Numbers, and I've done an awful lot. I did a session last week on the hundreds chart. If I take my hundreds chart, and I'm just gonna start this with you, just to give you a comfort zone. What kind of numbers am I highlighting right now? Say it, class. Miss Sutton, they're all multiples of 3. So I'm putting a chip on all the multiples of 3. I'm doing it in green because that's the colored dot on my number line. So I'm putting chips on my chart. Now I'm going to go away from green just for the sake of time. Here's where the real power comes in, because if you joined me yesterday for my upper grade games class, you heard me say single most important math skill that guarantees a child's success in middle school is their ability to factor numbers. If a child has to do long division to factor numbers, I can guarantee you it's not going to happen, because that does not motivate students. Let's go to the river on this pattern. Touch the 3. How many chips are in that diagonal? There's 3. What's the digital root of every number in that diagonal? Hold up the fingers. It's 3. Maybe that's an accident, class, and then your job is to chant back, there are no accidents in math. Touch the 6. How many chips are in that diagonal? 6. What's the digital root of every number in that diagonal? It's 6. Not an accident. How many chips are in the diagonal I'm touching? 9. What's the digital root of every number in that diagonal? 9. Now, if that pattern is going to be true about every multiple of 3, let's see what happens in this diagonal. Digital root is 3, 3, 3, 3, 3, 3, 3, 3. What's the digital root of every number in that diagonal? 6. What's the digital root of this little small diagonal? 9. Here's the thing, people. If a number has a digital root of 3, 6, or 9, you don't even have to check it. It will have 3 as a factor. Now, for every statement that I make that's positive, I've got to flip it and say the opposite. If the digital root of a number is not 3, 6, or 9, you can eliminate 3 as a factor, but you can also eliminate any factor that is a multiple of 3. So let me prove my point here. I'm going to turn to my 6 stick. We no longer eat on my kitchen counter, people. I'm just saying. It's now become my virtual classroom. So look at your 6 stick. You can see the only difference between my 3s and my 6s is on the 6 stick, I took off all the odd numbers. So let's find the digital root of 6, of our 6 stick. You have to say that slowly with upper grades, and I almost went too fast. Some of you get my humor. So let's find the digital root. 6, 3, 9, 6, 3, 9, 6, 3, 9, 6, 3, 9. If you've been with me in person, I do a human Venn diagram here, because the 6 rule to know whether 6 is a factor uses the 2 rule and it uses the 3 rule. Here's the fun thing, and this goes back to Catherine's question about a digital root of 9. Every multiple of 9 is going to have a digital root of 9. That doesn't mean there's anything left over after you take away all the groups of 9. Because I told you a digital root of 9 is the same as a digital root of 0. So put a reminder to yourself. 2 reasons to teach digital root. 1 is to determine or eliminate factors. The other one is to check all computation. So I have my trusty place value pocket, I have a 3-digit number. When I taught those games yesterday for factoring, this is how good I want my kids to get. I want them to be able to look at a number. Ooh, I see a friend with Sophie. Here's the fun part. I want them to be able to determine or eliminate factors without doing long division. So you can tell by looking at this number, 5 is a factor. I know that 2 is not. And if you played the games yesterday, we learned that if 2 is not a factor of a number, you can eliminate any factor that is a multiple of 2. Now I want to see if 3 is a factor of this number. So I'm going to find the digital root. 4 plus 3 is 7, plus 5 more is 12. What's the digital root of 12? 3. So I know without even doing the division, 3 is a factor of this number. Put a note, the second reason to teach digital roots is you can determine or eliminate factors of numbers. I know I have to wrap because you have other teaching to do. Couple of little reminders for you. We will post this up on our YouTube channel, Creative Mathematics, this afternoon. I love talking about this. I hope you could tell how giddy I was. Here's the fun part. I feel compelled at some point we will do another deeper session of digital roots, and I will ask you to wear your seatbelt because we're going to hit a lot of turbulence because I'm going to teach you even more. So, couple of reminders. Next week, I will not do a live session on Wednesday. I apologize for that. We are filming a 2-day staff development training that will be available this summer because we're having to shift my summer schedule, which was completely booked up June, July, and August with workshops for districts and workshops for people signing up. We are switching to virtual trainings. So I want you to watch the website because next week we're going to film a 2-day training that is my 10-block training for MathFact Fluency. And that was to be done all over North America this summer, not only by me, but by my KSAs, but it will be only done virtually and it will be done by me. So we're going to be filming that next week. So my encouragement is I am planning to keep myself very busy this summer, but it looks to me, I mean, we're not there yet with definite plans, but it looks like it's all going to be virtual training. Virtual trainings that we offer through Creative Mathematics. I'm not talking about the work I'm going to do with the school districts. Those all come with college credit as an option or clock hours. So be aware that those trainings will be done virtually. I know they're not as fun, but you know what? All of my virtual trainings through Creative Math, you're going to get sent the materials, the manual, the toolkit, all of those amazing things that I give out. So they'll be a part of our training. So I want you to watch that because that's coming up. I will be doing a lot of school district trainings and it looks like those will be done virtually. So we do have a lot planned and I'm excited. I'm old dog learning new tricks as we all are and learning what it's like to teach virtually, but this is where we are and I'll keep working on it, people. I think we should close with a song about digital roots. Oh, one question, Josh says.
Amy wanted to know what you call the triangle relationship instead of factoring.
Inverse relationship to the operations. So Amy's question was, what do I call it instead of calling it fact family? I call it, so I would call the inverse operation. So when I do those triangle flashcards, I say to students, multiplication, the inverse of that is division. And then I go through that relationship. So I'm really speaking the language and that comes from having been a teacher of middle school kids. I mean, they have to hear it correctly. Fact families is a very friendly term. If you want to, you can say fact families, and that's inverse. But I would recommend you talk about it as an inverse relationship. So shall we do our digital roots song? Say yes, Miss Sutton. Say, we're so excited we can hardly stand it. I want to thank you for joining me, and I'll look forward. I promise you more things happening, but next week we have that filming. So let's close with the digital roots song.
Digital root, can you find the digital root? Digital root, can you find the digital root? The digital root of a number is the sum of all its digits. Keep adding that sum until you're done, and a single digit is the final outcome. That's the digital root.
Punch it out, people.
Digital root. Can you find the digital root? Let's take a number like 53, add the 5 to the 3. The sum is 8. You're doing great. The digital root is 8. The digital root is 8.
Here we go.
Digital root. Can you find the digital root? Let's try 571. Add 5 plus 7 plus 1. The sum is 13. Add them once more, and soon you'll find what you're looking for. The digital root is 4. Digital root. Can you find the digital root? 3,483. Add them all together, 18 you'll see. Add them once more, 9's the score. That single digit's what you're looking for. The digital root is 9.
Here we go.
Digital root. Can you find the